Welcome back, everyone. In the previous video, we left off with us graphing the raw attention scores when the query vector belonged to river. So just a quick recap. Remember, this is the query matrix, and if we look at it, it's this query matrix, and this doesn't change whatever the input is. These are learned weights that are going to apply a linear transformation to the embedding vector, okay? This, however, does change. This is the query vector for river. So when the model is focusing on the word river, it's going to, learn it by using the query vector of river, and it's going to be multiplying it with the key vector of the other words in the sentence. Okay? And if we come back over here, this is where we're at. We had the query vector of river, and we multiplied it with the key vector of every other word in the sentence, and that gave us raw attention scores. So we're right over here at this matrix multiplication. And over here you see this, and this is a softmax. So we're going to have to use softmax and apply softmax to the scores. And this step transforms the scores into a probability distribution, ensuring that they all add up to 1 and mitigating large variances in the scores. So this will help gradient descent and backpropagation, speed up the process. It ensures that we don't have the vanishing gradient problem. And if you don't know what softmax is, it's a squashification function, as you can see over here. And what it does basically is you have these output values, and you apply the softmax activation function to it, and it just gives you back the values, but in probabilities. So as you see, for example, this 5.1, this became 0.9 because 5.1 was a large value, so it became a large probability. And you do this by basically summing over all the outputs, and that's going to be the denominator, and then you take the numerator for every single output. So for this first one, the numerator would be 1.3, and the denominator would be the sum of all these values. And if you do 1.3 over the sum of all these values, you get 0.02 for the probability output. Okay, so it's not a difficult function, and it ensures that backpropagation and gradient descent are fast and are optimal. So over here, we convert these raw attention scores using softmax. So over here, you can see convert scores to weights using the softmax. So what we're doing is, think of it this way. We're taking these values, this negative 0.74, negative 2.58, 0.204, and we're basically doing this exact same thing with it, okay? We're going to sum them all up, and then we're going to look at them individually to see the probability, okay? So this is the softmax function defined, as you can see over here. So you take the sum of all of the inputs here, you raise them to the power, you raise e to the power of these scores. So, I lied to you guys. It's not as simple as just adding these up. You have to add them up, but they are going to be the exponent of z. So this 1.3 is not going to be simply 1.3. It's going to be e to the 1.3. And then we add e to the 5.1 for the denominator. And then we add e to the 2.2. Then we add e to the 0.7. And this last one, I believe, is 0.1. You can't see it from this icon, but you would do e to the 1.1, and that would give you the denominator. You're just summing up all the values, but before you do that, you're just applying the e function, okay? And over here, we have the given raw scores. So the step-by-step calculation. We first compute the exponentials of each score. So over here, we're just raising e to this score. We're raising e to this score. We're raising e to this score. So basically, I don't think that's too complicated, and you guys and girls are all smart and you understand what we're doing over here. Then we sum all exponentials. So we sum all of these. We take this plus 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 this, and then we divide each exponential by the sum to get the normalized weights. Okay, so first, the sum of all exponentials of the raw scores is calculated here. So over here, 8.0128 is going to be the sum of all these values. So if we add this plus this plus this, we get 8.0128. So this is going to be the denominator, okay? And then to get the actual softmax weight value, you just take the current word. So over here we have the softmax of the CLS token. And remember, the CLS token has this value, okay? Because we're just taking E and we're raising it to the raw attention score. So E to the negative 0.774 is going to be the numerator. And then we divide it by the denominator, which we calculated over here. So you get 0.0576. And you do the math for all of them, okay? And why this is nice is this ensures that all these values, so 0.233, 0.1374, 0.1248, and so on, if we add them all up, they will add up to 1, okay? And that will give us a probability distribution. So that's what we're doing over here. The math is, you guys and girls have understood a lot harder math in the previous lessons. So over here, for example, this negative 0.258 is the raw attention score of the, okay? It's the raw attention score of the. Okay, so that's going to be used as the numerator, and we're going to get this probability. So if we look at it basically right now, this is just a probability distribution. So when we're looking at the word river, as we discussed, it has a high attention score with itself to retain information. But if we look at bank, it also has a high attention score, 0.153. And flooded also has a high attention score. So the order remained the same. Remember, over here, if we come back over here, river had the highest attention score with 0.216. Then it was bank with 0.204. Then it was flooded with 0.096. And if you look at the probability distribution, river has the highest probability output. Then bank has the next highest. And then flooded has the next highest, okay? So over here, you can read that these values represent the attention weights for each token, influencing how each token's value vector contributes to the overall output of the attention layer. So these values will be used as weights for aggregating value vectors in the attention mechanism. Now, if that didn't make sense, just keep in mind that we are over here and we still have this value vector. So we're going to be multiplying these final outputs with the value vector. So that's what this part means, that these values will be used as weights for aggregating value vectors in the attention mechanism, okay? So over here we have the array of final softmax weights. So this array is just an array of these values. So it starts with 0.0576, 0.0576, and ends with 0.1233, which comes from over here. And as you can read, each element in the array corresponds to the softmax calculated weight for each token's attention score, used to modulate the influence of each token's value vector in the output of the attention layer. So we're going to use these weights and multiply them with the value vectors to get the final context-aware representation of each word, okay? So what we've done essentially is just we've taken these raw attention scores that we calculated over here, and we just converted them to probability distributions, okay? And that will help the model speed up training and ensure that there's no issues with vanishing gradients or exploding gradients, so just things like that. And in the next video, as you can see over here, we're going to start talking about the value matrix, which is over here. Okay, so I will see you in the next video.